This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
General relativity removes fixed coordinates, and quantum gravity allows these flexible, shifting space-time geometries to exist in superposition. When these structural branches overlap, there is no mathematical rule to dictate which point in one geometry corresponds to a specific point in another. This creates a systemic mapping failure, known as the alignment crisis. The alignment crisis is a condition where covariant superpositions lack the necessary correspondence to establish consistent physical locations or distances across branches. Without an operator to resolve this geometric ambiguity, the single stable spacetime we observe cannot mathematically form from the superposition. As these unaligned spacetime branches evolve, the mismatch between their internal structures accumulates. This chart tracks alignment entropy, measuring the exact degree of structural degeneracy, or the number of viable correspondences, between superposed geometric states. When the degeneration becomes too severe, the system reaches an exact mathematical boundary called the critical threshold. Crossing this threshold forces the overlapping geometries to collapse into a single state to eliminate the accumulated ambiguity. Past models treated wave function collapse as an ad hoc or random event. Under this framework, the reduction is a required deterministic response to unsustainable geometric pressure. The selection of a classical reality is an optimization protocol triggered by this specific entropy limit. This formula represents the stabilization operator, omega. It executes the collapse by identifying the single admissible history from the superposed set. It minimizes an instability functional, weighing gravitational self-energy and spectral turbulence, the numerical fluctuations in the geometric spectrum across divergent branches. The calculation is governed by a strict constraint called ordinal descent. Ordinal descent is a mathematical rule requiring each step of the stabilization process to move strictly downward in complexity rank. Because a sequence cannot descend infinitely, the protocol is mathematically guaranteed to terminate. Ultimately, the framework ensures that the system will output exactly one definitive classical state, completely avoiding any infinite loops. This structural framework translates directly into testable laboratory conditions. Researchers test this by placing levitated nanoparticles into quantum superposition inside optomechanical resonators. An optomechanical resonator is a device that uses light pressure to control and measure the mechanical vibrations of microscopic masses. This scatter plot compares the system's gravitational energy proxy on the x-axis against the required collapse time on the y-axis. The data points form an inverse scaling curve, demonstrating that higher mass distributions force the superposition to stabilize faster. By defining the exact threshold where geometry breaks, the stabilization operator provides a physically falsifiable blueprint for the emergence of reality.